Today I want to talk about the geography of global warming. And before I start, let me thank the Becker-Friedman Institute for organizing this. It's great to be here. It's great to be with all of you. I'm new to the University of Chicago. I just moved here from Princeton. And the work that I'm going to present today and some of the details of that work are joint work with a graduate student that I had at Princeton, Jose Luis Cruz. So this topic of the economic geography of global warming is it's obviously kind of of great interest, kind of in an abstract way to all of us. We all want to try to understand kind of the impact that global warming and more generally climate change is going to have on the economy and on other aspects of the life of humans in this planet. I'm going to limit my approach to think about the economic implications of climate change and global warming in particular. Of course, there's many other aspects, and so let me just preempt by saying, you know, I'm not going to touch on those aspects, and of course they are there, and the fact that I'm not addressing them directly doesn't mean that they don't matter or they don't exist or are in some sense take second order relative to what I'm going to talk about. Okay, so we all know about the basic phenomenon. There's CO2 concentration in the atmosphere the CO2 concentration has risen rapidly since the mid 1800s. That's, you know, has been attributed and is, you know, very clearly attributable to human behavior. So the industrialization, transportation, and other forms of economic activity have generated CO2 emissions that have accumulated in the atmosphere at unprecedented levels, and that has led to increases in temperatures. So here I have two graphs from the IPCC, the Intergovernmental Panel for Climate Change, the latest report that they brought out. This shows the very, very long-term perspective, so over thousands of years, and you see kind of the big peak in temperatures at the very last part, in the very last part of that period between 1850 and 2020. And on the right-hand side, you see the actual changes since 1850, so kind of a zoom in on this part of the graph, and you see the big increase in the actual temperatures. And here is also like their attempt to say, well, what's kind of the contrafactual scenario in which, you know, humans didn't generate all these CO2 emissions? What would be the temperatures? That's the green curve there, and the confidence intervals around that. So you see, you know, there's obviously the brown ones are much higher than the green ones, meaning, you know, humans and their actions have generated increases in temperatures. And so that part is by now uncontroversial, and even though there's certain uncertainty about how big this effect is, as you can see from the kind of confidence intervals around the basic the point estimates, you know, we're very, very, very confident that effect is there and that it's relatively large. Okay, so that's the basic science of this, or the basic fact that we know. Now, what we want to try to understand is what's the economic impact of this, right? Which is, of course, very different than what is the science of the phenomenon itself. To what extent temperature has reacted to the CO2 emissions or cumulative CO2 emissions that we've seen in the history of the industrial world. These graphs are about the science, not about the economics. We want to try to understand what's the economic impact of this. Now, the basic point, there's a basic point here, which is that CO2 emissions are a global externality. So what do we mean by that? We mean that, you know, there's individuals and firms that act and use carbon or emit carbon, use energy that implies production that generates CO2 emissions, but these CO2 emissions then very quickly mix in the atmosphere and affect global temperatures and in general climate in the world, not the climate of those particular regions, right? It affects the world overall, and so because of that, individuals in particular regions or firms in particular regions do not face the full consequences of those emissions, right? Because they affect the climate everywhere in the world. And so because of that, because they don't face the full impact of their decision to emit, this is what we economists call an externality, right? You don't face all those effects. And that is in itself a justification for policy. That is, already sufficient to say we want to act and we want to do something about this, because the market itself, if we just don't do anything, right, that's not going to be an efficient solution, because everyone is going to emit more than what the socially, or from the world's perspective, we want them to emit. And so that already invites, the role for policy. And so I know that everything that I'm saying is very basic, so we're just warming up, okay? So we want policy, but of course every time we want to, this justifies policy, but it doesn't justify what policy, how big should that policy be, right? How many resources should we actually spend on this, right? It doesn't tell us anything about that. It tells us there should be policy, we need to address this somehow, but it doesn't tell us about the exact policy or the magnitude of the problem that we need to solve, okay? And so what this research that I'm going to show you is about is trying to, kind of the premise of this is, well, we need to think about how big this phenomenon is, because if we as a society are going to go and dedicate serious resources to address this, right, we better know how big what's the magnitude of the economic effects that this will have, what are the potential policy solutions, what's going to be their impact, so that we can compare with the many other needs of society, right? Because there's all sorts of other needs. We also need to solve pandemics. We also need to help develop, the parts of the world that are underdeveloped. We also need to help the people that don't have access to all sorts of different services, etc. There's many policy needs in the world, right? And so in order for us to assess the needs of society, we need to evaluate this phenomenon. We cannot avoid that step. That step is essential, right? And so that's where kind of this research comes in. Now, when we want to think about how to do that, what is going to determine the economic impact of climate change, the point that I want to make here is the following. How costly in economic terms is global warming, or climate change more broadly, depends directly on the cost of moving economic activity across locations, of changing the places where we live and where we work and where things are being produced. And so what's the argument? What's that argument in a nutshell? In a nutshell, the argument is, well, there's a wide range of temperatures in the world. The increases in temperatures that we're talking about from carbon use, etc., in the most extreme scenarios, and we're talking very extreme scenarios, are going to say be 7 degrees Celsius over 400 years, right? That's very extreme, right? But it's still clearly within the range of temperatures that we see in the world. And so what that, the kind of obvious implication of that is that, yeah, this is going to be terrible, devastating for some areas of the world, right? But for some others, you're going to move them from 0 degrees to 7 degrees, and that perhaps is not as bad, okay? And so that heterogeneity matters because, of course, if then we can costlessly take economic activity and move it from where it is to places that are not going to be as affected or are actually going to be even better off, then if we can do that cheaply, then this wouldn't be a big problem, right? We just do that and that's it. Now, of course, you can come and tell me, no, but moving economic activity is really costly. And I agree with you, it can be quite costly, right? But my point is that it's going to depend on those costs. The overall effect or impact or economic impact or cost of climate change is going to depend on that. Now, another way, I think that you could tell me is, well, maybe we're just run out of land, right? Out of productive land. And if you kind of desertify a bunch of the areas that the world can use to produce, we're not going to have enough areas to produce. But the reality is that most land in the world is just not economically used. It's essentially economically empty. So there's plenty of land. That's not the problem, right? There's plenty of land. And so at the end of the day, where do we end up then? Well, it is going to be about moving economic activity out of some coasts because there's going to be sea level rise, moving economic activity from some parts in Africa, etc., that are going to warm up to a level where it's going to be very hard to live and produce there, right? But it's all about moving that economic activity and how costly that process will be. Now, you can say, well, yeah, but I mean, people just stay where they are. We've never seen this. And so, you come here and you tell us that all this, we are going to move, the whole distribution of economic activity across locations, but I think that's completely unrealistic. And so here's my answer to that, which is, well, we've seen it before. And we've seen it not in this modern society where we can take planes and move and do all sorts of things. We've seen it in the 12th and 13th centuries, in the medieval warm period, where temperatures grew by 2 degrees, say, roughly, right? And that implied, big changes in the societies at that time. So Mesoamerican and Khmer societies and the Khmer Empire declined partly because their physical circumstances around them became much worse because climate was warmer, but it was actually pretty good for Nordic societies that, and allowed them to grow in terms of size, but also in terms of their settling in other places like Iceland, Greenland, etc. It also helped the Mongolian Empire to expand. That's the kind of whole story of Genghis Khan. And so these are just examples. I mean, if you want more examples like this, go to that book by Brian Fagan about the medieval warm period that exactly goes through all sorts of stories and how this movement for different groups was related to the changes in climate that happened during that medieval warm period. So, adaptation, if those societies back then could adapt, imagine our current societies, right? If anything, it should be simpler, right? Okay, but it's obviously not free, and so we still need to think about how to bring that all together in models in which we can take into account those costs, the fact that it's costly, and the fact that individuals are going to make decisions and are going to be adapting in order to avoid the worst effects of this type of phenomenon. Okay? And we're going to do that. And so it's very important for us to build these behavioral models that explicitly model the behavior of both individuals and firms so that we can really think about the very long term, when all of this is going to really matter, right? When all of these effects are going to accumulate to lead to a world that is going to be quite different in terms of its climate potentially, right? And so we need to think about all of that behavior and how that behavior can lead to a very different world. And it's just not enough, or it's not necessarily the best methodology that we can put forward to simply extrapolate from the effects that we've seen so far. Just because that world and those effects are going to be very different than what we've seen so far, right? So extrapolating just empirically from measurement from what we see today is kind of difficult. Okay, so I'm going to show you the results of such a model that includes those behavioral responses, right? And it's a model that is going to generate kind of a pad of CO2 emissions, so in the quantified version, that is going to be very similar to the scenario. I mean, for those of you that know a little bit about this, the IPCC puts out scenarios, some more extreme than others. The most extreme kind of business as usual scenario where there's no policy to really address carbon is the RCP 8.5 scenario, which is like the dashed line here, and the green line is the outcome of the model that I'm gonna be showing you, and that leads to an evolution of temperatures. This is kind of the numbers that I was quoting before, that is also close to that scenario in the IPCC. Now, so this is the type of increases in temperatures are large, that are gonna underline all the results that I'm showing you, are quite large, in line with the worst case scenarios of the IPCC models. Now the key is going to be that these increases in temperatures affect local areas of the world very differently. And they affect local areas of the world very differently because of two main reasons. One is that when average temperatures grow, local temperatures don't grow by the same amount. They grow, but differentially, depending on where. This is what is depicted here in this map. So a 1 degree Celsius increase in global temperatures implies a 2 degrees Celsius increase in temperatures in the very red areas here, but only a half degree increase in temperatures in the very blue areas in that map. Okay? So very different local effects on temperature from global effects on temperature. That's the first reason why these kind of local effects are going to be so different, so heterogeneous across locations. And then the second reason is that, of course, it's not the same to get, if my location gets warmer if I'm in the Sahara than if I'm in the tundra, right? It's very, those two, the effects of increases in temperature in different parts of the world are different because, you know, the base level of temperature, of course, matters for how big, how damaging that effect can be or not. And so, in a nutshell, so I'm not going to show you the model in detail. We don't have time for that. But let me just, so that you get a little bit of a sense of how things work, let me try to explain with this diagram. So there's going to be people and firms living in all these different regions in the world. And the resolution that I'm going to be using is the resolution that you see in this map. So a pixel in that map is what I'm calling a location. Okay? And so there's many thousands of those in that graph or in those maps. Okay? And there's in each one of those, there's people and firms. People are living there. They own the land. They are supply that land for production, and they supply labor. They work, right? And then there's firms, and these firms are going to be producing goods using labor, land, and energy. They are going to produce particular goods that they are going to trade, subject to trade costs, with the rest of the world, and they're going to potentially innovate. They're going to improve their technology. They're going to spend some resources to improve their technology. And their incentives to do that, to innovate more or less, depend on the market that they have. How big is that market? So if you live in the middle of, or if that firm is in the middle of a great concentration of economic power or economic or lots of aggregate consumption in that region, well, then you want to innovate more. Why? Because I only pay once for innovation, but I can use it many times to supply all the goods to everyone, right? So there's, you know, innovation is a big economies of scale kind of activity. Okay, so that's these firms. And these firms then have a particular level of productivity, how good they are at transforming inputs into output, right? And given that, they're going to pay some wages for labor, rents for land, and agents then are going to take those wages, rents, they're going to consume with those, and they're going to also experience some benefits from the characteristics of where you live. So if you live in a really nice area with really nice weather, for example, you enjoy it, or if you live in a nice city, You enjoy it relative to living in a place that is maybe more arid or not as not without as many amenities. And so the economic gains from living in a particular place, plus these kind of utility benefits of being in a place that is kind of nice to live in, are going to determine whether individuals want to be there or want to move away to some other location. And if they move away to some other location, they pay cost. They pay migration costs in order to do that. Okay? And so that is the kind of the core economic model. And then, you know, there's these firms use energy. Energy in turn can be produced with clean and fossil fuels. If it's produced with fossil fuels, which is a decision of these firms, then that generates CO2 emissions, which increase the stock of carbon. That's what we were discussing before. That has an effect on global temperatures, which in turn has an effect on local temperatures, but heterogeneous. That's what we were saying. And then importantly, these local temperatures are going to have three key effects: on productivity of these firms, on these amenities, right? How nice it is to live in a particular location, and potentially also on birth versus death rates through, for example, effects on health and things like that. Okay? So that's the core of the model. And then you can quantify this model so that this economy matches exactly what I see in the world today. So output levels in the world in each one of these cells, population levels in each one of these cells, the fact that these cells trade the right amount between them, the fact that mobility across areas of the world captures what we see in the data as well. So you can inform this model with all, so that you match exactly how the world in some sense looks like today. Okay? And so then the exercise that we want to do is we want to say, okay, let's run this model, right? And see how is the world going to look like in the future if we just let this model work with climate change or without climate change. And so we can compare those two scenarios. Now, in order to do that comparison, we need this model because one is a contrafactual scenario, a scenario where climate change doesn't happen, or a scenario where we impose some policy that otherwise we wouldn't have. Okay? So we need to do these contrafactual scenarios. For that, we need a model that has these things. Now, one key part of that model, one essential core part of the quantification of that model, is those local effects. To what extent changes in local temperatures are going to affect productivity, the amenities, and those natality rates, right? Those are the direct effects of higher temperatures in a location on the characteristics of that location for economic activity, either living there or producing there, okay? So we want to know that, and so what we can do is we can use the model to read out of the data what the local amenities and productivities are over different periods of time, so say in this case over a 20-year period, and that gives us what we call a panel of data on productivities and amenities in the different parts of the world. Namely, we have the level of productivities and amenities for every period, right, in each one of these locations, okay? And then we can say, well, conditional on that, what's the effect that climate changes or in particular temperature, local temperatures, have had on those amenities and those productivities? We can measure that, right? And we can allow for different local characteristics, fixed effects, etc. So we can do that in a kind of fairly detailed way, and this is what comes out of that. So what I have here, this is the effect on productivities, this is the effect on amenities. Let me focus on the effect on amenities first, right? So this is the amenities that come out of this exercise, and what I have here is the impact that temperature will have on the amenities of the different locations ordered by their initial temperature. So this is initial temperatures in winter, so here it would be in January, and so these are the coldest places in the world, and those are the warmest places in the world, right? And so what is this number 0.025 telling you? It's telling you if local temperatures in that particular location go up by 1 degree Celsius, what's the percentage change in local amenities, right? And what this 0.025 tells you is, the answer to that is 2.5%. So if you multiply by 100, that will give you the percentage. So, so namely, in the coldest places in Alaska or Siberia, when temperatures increase, right, what happens? Amenities go up. Right? This is not imposed on anything. It just comes out of this calculation that I told you about. Now, it's very different in the warmest places in the world. In the warmest places in the world here, right, if you increase local temperatures by 1 degree Celsius, right, amenities actually fall, right, and fall by a little bit more, but about the same, but not that different, right? And you can see that, you know, something very natural comes out of this. I mean, this is not, again, imposed in any sort of way. It comes out of the empirical exercise, is that, you know, in the coldest places in the world, increases in local temperatures are beneficial. Then eventually that crosses zero. So those places, the effect is very small. And then in the warmest places in the world, increases in temperature are detrimental. They are bad for amenities. And the same is true for productivities. You can see the differences. If anything, for productivity, the effects are larger. So you see in the warmest places in the world, an increase of 1 degree Celsius in local temperatures, decrease local productivity by about 15%. So that's big effects, right? That is a really big effect. Now, of course, what happens when that happens, people are going to react to that. And we want to think about that reaction and what that reaction does. Because ultimately, like we said, the overall cost of climate change are going to depend on that reaction. This is just to tell you, you know, if we take those damage functions and look forward, so this is, you know, by 2200, how would amenities look like relative to a world in which there is no global warming, in which temperatures are not changing, right? One means there's no effect, zero effect. Everything that is blue is there's negative effects. Everything that is red means positive effects. So what do you see? You see in Siberia, you see in northern Canada and Alaska, you see positive effects, but then in South America, Central America, and parts of Southeast Asia, you see negative effects. And the same is true for productivity. And so this map is a kind of, I'm going to show you a lot of maps that kind of qualitatively look like this, where the areas that where productivity or amenities are lower are these ones, and therefore these are the areas that are going to be losing, and then, you know, these areas over here are going to tend to gain. So these are the outcomes. Once people adjust, etc., what happens to population? Well, of course, population is going to start moving to these other areas, so everything that is red there, and where are they going to come from? What are the areas that they're going to leave? Exactly those areas here in these regions of the world that I mentioned before. In general, what this tells you is there's going to be 600 million climate immigrants by 2200. That's what this model would predict. 600 million people are going to be in a different location because climate change happened. And that, of course, is going to have an impact on the local economies. This is the effect on real GDP, on real gross domestic product of the different locations. And you can see, you know, the big effects are, again, where Central Africa, South America here, and parts of Southeast Asia, similar map to that. You can also think about welfare, where you take into account those effects on amenities that we were talking about, right? But the map overall looks similar. Look at the scale here for welfare. This is telling you the locations that benefited the most are going to, you know, welfare there is going to increase by about 15%. The places that are going to be hurt the most, welfare is going to decline by about 15%. So Africa, right, and that parts of Central Africa are going to be much worse as a result of this, but parts of Siberia are going to be better off. This is the distribution across locations of those impacts. And you can see that this is like a two-peak distribution, right? It has like a lot of mass here and then a lot of mass here. This is the rich world. This is Europe, the US, all the rich countries that are going to be affected, but not so much. 1 would be no effect. Greater than 1 means positive. Less than 1 means negative. So this is negative. They're going to be affected, but relatively little. And then this big peak here, this is Southeast Asia, Africa, and Central America. They are the places that are going to be most affected. And you don't have to be an expert in the geography of economic activity in the world to know that everything that is blue in those maps, those are the poorest areas in the world today, right? And so obviously, if I'm telling you these places are going to be very badly affected, while these places here are not, and then the rich world is kind of at the cusp where the effects are not going to be that large, right? That this is going to increase inequality quite a bit. And in some sense, this is exactly the main story. The big story is about this change in inequality. The fact that this phenomenon, the main effect is going to be this increase in inequality by which some regions are going to be affected a lot, but those regions happen to be the regions that are the poorest in the world today. So just to put that in perspective, or kind of give you a little bit more of a sense of that, I have this graph here where I've ordered things by real GDP per capita, and what you have here is the effect of climate change on the different points in that map. 100 means no effect, greater than 100 means benefits, lower than 100 means, 95 would mean a 5% decline, right? And this is, the colors are different parts of the world, you can see them there. And the size of the dots is the number of people that live in a particular area. So what do you see here? You see kind of a clear positive slope with Sub-Saharan Africa over here, Southeast Asia over there, and the OECD and the richer countries up there. And this slope, the slope of this line is is exactly 0.015, and it's in a log scale. The x-axis is a log scale. What does that mean? It means when you move from, say, 0 to 1, is like doubling real GDP per capita. It's not a mathematically exact statement, but good for thinking about the graph, okay? So if I move from 0 to 1, you're doubling GDP. So these are areas, the areas that are here have half the GDP of areas that are over here, right? And so if you have double the GDP, the effects on you are about 1.5% lower. The effects from climate change, the negative effects from climate change, are going to be about 1.5% lower than for a country that has half your income. So that's telling you, the poor countries are much more affected, and it tells you kind of the rate at which that changes as countries have higher income. That's not because they have higher income, but they just happen to be in places, right, that are less affected by this phenomenon, and as a result, they're receiving some of the immigrants and some of the investments that result from this. Okay. So now I should mention that, of course, everything that I'm saying there's a lot of uncertainty, right? How can there not be uncertainty? We're talking about predictions over hundreds of years. Of course, there's huge amounts of uncertainty about these estimates, right? But they still give us a good sense of magnitudes that we need, that it's important to have. So this is just to give you a sense of uncertainty. The point estimates for the world in terms of losses in welfare over time is the dark line there, right? But the 95 confidence interval, if you take into account the uncertainty in estimating these local damages, is quite wide. You can see it goes from about 0, right? So 0 effects to effects that are as large as 20%. So by 2100, by 2200 here, the effects are expected to be about 11% or so, but we don't know with 95% probability, they could be between 0 or say -1 and about -19. So that's kind of the range of potential outcomes that we need to consider when considering the impact of this phenomenon on average. Now there's also the dispersion across locations that I was talking about. Here are the distributions of the effects across locations. You already saw the intermediate one there. These are for kind of best case scenarios and worst case scenarios. And these distributions change depending on what scenario you're considering, of course, but the range of the cost doesn't vary that much. That's to say, the extent to which this is going to increase in inequality, we're kind of pretty sure about that, right? What we're not so sure is about what's the level of those effects, as I emphasized in the other graph. Okay, so let me take a couple of minutes to talk about adaptation, then I'll say something about policy, and then we can start the conversation and the discussion. Okay, so the first thing, so one reason why these effects are not as large as the direct effects that I showed you, right, is that people are going to react, like we said, right? They're going to move. So if your area becomes worse now that it's warmer, then a lot of people are going to move. And so we saw that they're moving away from these parts of Africa, etc., and South America into the northern latitudes, right? So those are the climate migrants that are generated by this. And so, of course, naturally to think about, well, how important is for migration costs to be low so that these people can adapt and we can keep the cost of the phenomenon low, right? And so what this exercise does, it says, well, how larger would the cost be if we increase migration costs? If, as this happens, nations start saying, well, let's close our borders, let us not allow anyone else in, right? So if the US immigration policy gets more stricter, Canadian policy gets stricter, European policy gets stricter, if that happens, how much larger are going to be the cost of climate change, and where are we going to see them? Right? And so what this is telling you is, well, if you increase those migration costs, the red areas are going to be worse off. So obviously, Siberia or northern Canada, they're going to be worse off because they are benefiting from the migrants that are coming in and the development of those areas where, today there's very little, right? And Africa and Central Africa is going to benefit, or is going to be worse off if you increase migration costs. Why? Because they benefit from sending migrants to those places, right? It's a great safety valve for them. That migration is great safety valve for them. But look at South America. Now suddenly Africa and South America are very different. The effects are very different. Why? Because for South America, if you increase migration costs, it's actually not that bad. Why not? Well, it's obviously harder for their people to move to other places, right? But it also keeps more people in the area relative to scenarios in which lots of people leave, but when they leave, they also, the area kind of loses critical mass for development. So these are areas where you kind of want to keep more people, because if everyone leaves, then there's not enough economic activity there for development. Look at Australia, same thing. So higher migration costs in some sense help some areas, actually hurt some others, like Africa and those northern latitudes. Overall, it hurts the adjustment process and therefore makes the cost of climate change much larger, right? So the red areas end up dominating the areas that are not so red in that map. And so migration is an important adaptation mechanism, and not having the cost of migration not increase as we see this phenomenon happen is very important in order to diminish or decrease the cost of climate change. A couple of words on policy. Okay, so now we have the model. The model produces these outcomes that I've been talking about, and now what can we do? We can use it to introduce different types of policies and see what's the impact of those policies. What can these policies do, right? So here, what I did is I started with a carbon tax. So the carbon tax is obviously kind of the most natural policy in this context. Why? Because it's exactly a context in which the private value of those emissions is different than the social value of those emissions. And so a tax, if you put a price on carbon, you bridge that gap, right? And so that's the kind of basic economic logic. And so we can do that. We can impose a tax in the model and see what would happen if you impose the tax. And so if you impose the tax, say you go from the baseline case and you impose a tax as large as as the Swedish tax, then you would go to the bottom line here. And the other cases are in between. Okay? So obviously you impose the tax, there's less emissions, right? And so that reduces temperature increases over time. And so you move from this curve to that curve. And so that's great. Temperatures go down. And so the negative effect of temperature, it's smaller. Now what you also see in these curves is that eventually that effect kind of goes away. Even though we're not taking away the tax is still there. So why is that? What's happening? Well, what's happening is that at the end of the day, carbon is a finite resource. Right? We can only use so much carbon in the world. Now, if I impose a tax, you consume less carbon, that works, right? You will consume less carbon, but because you consume less carbon, in the future, extracting carbon and using carbon is going to be relatively more costly, right? So without the tax. So meaning, if you impose the tax, because you consume less carbon, right, there is more carbon available, and so extracting that carbon is cheaper, and so the fact that it's cheaper, it kind of cancels, in some sense, that tax. And so that's why these curves eventually cross. So where is that effect coming from? It's coming from the fact that the more carbon you extract, the more costly, in relative terms, relative to clean energy, carbon extraction becomes. And so what's the ultimate effect of carbon taxes is just to reduce temperatures, but mostly to flatten this temperature curve. You see how it's lower, but it's kind of flatter, right? You kind of start from the same point, and you end up more or less in the same point, but throughout the levels are smaller. Now that's useful, right? But certainly not as useful if you had an overall effect on the total amount of carbon used. What's the sense in which it is useful? Well, it has cost today, so these are the relative costs. It has cost today, but it has benefits in the future, right? And so when we impose carbon taxes, we are essentially doing this intertemporal trade-off. It's costly today, beneficial in the future, particularly beneficial in the future because of the growth effects that it's going to have in certain parts of the world. Now, because at the end of the day you're kind of essentially just flattening the curve, right? The effects are large, but not as large, right? And so really the best combination is one where you combine it with some sort of abatement technology, right? So think about it. The analogy is, there's a good analogy with the vaccine, the COVID vaccine. It was good to go home to flatten the infection curve so that not so many people got infected, etc. But why was it that good, in principle? Well, it was good because we were waiting for the solution. We were waiting for the vaccine, right? If the vaccine was not coming, then sending everyone home was not so useful because at some point, whenever we all got out, we would get infected anyway, right? So it was a measure that was useful while we waited for the solution. And carbon taxes kind of have a little bit of that flavor as well. It's very useful while we wait for an abatement technology. And in fact, if this is the case, if there's an abatement technology forthcoming in 2100, then these effects are much larger, and as these effects are larger, the benefits of the carbon tax today are much larger because waiting helps. In that case, waiting helps a lot. Not having high temperatures now helps a lot because eventually the solution comes and we can kind of capture carbon from the air. And so, combining this with policies that make that the arrival of such technologies better or more likely is kind of important. Okay, finally, There's clean energy subsidies. In this world, clean energy subsidies have the problem that, yes, they increase clean energy use in terms of shares, but also make energy cheaper, and as a result of making energy cheaper, make the world consume more energy overall. So there's kind of that effect relative to, combined with the relative effect. They both go in different directions, and so at the end of the day, as you can see, that has small effects on overall temperatures, at least in the quantification that we have. Okay, so let me stop there to take some of your questions in the last few minutes that we have. Let me leave you with these 3 points just to reiterate. Important to do the policy evaluation. We cannot make it a categorical issue. We need to do anything to, no, it's not anything. We need to think about exactly what is the value of the particular policies and what is the cost at stake in order to be able to effectively argue that is more important than other priorities for society. And if you do that, the key issue is that the effects are very heterogeneous in space and affect the poorest regions more. Okay? And then the solution is, we need to talk about carbon taxes, but we need to talk about other forms of abatement technologies as well.